In the deepest dark of space, growth can be quiet and relentless. Black holes do not become giants through a single dramatic event. They build through cycles of feeding limits and long pauses. Tonight's journey follows how seeds form, how inflow fights rotation, how light sets a pace, and how some cores become billion solar mass monsters over cosmic time. If this calm science sleep documentary helps the mind unwind, please like the video and subscribe for more long-form space stories. Settle in now. The universe moves slowly and the night can too. A black hole grows by turning ordinary matter into a one-way inward drift. The simplest path is steady accretion, guided by the gravity and limited by light. In a cold region of gas, a tiny dense seed sits inside a faint haze. Around it, a thin rotating sheet begins to form. The sheet is not flat for long, it thickens into layers where density changes with radius. Closer in the flow becomes smoother and faster. Farther out it looks grainy and uneven. A dark boundary exists at the centre. No surface marks it. The boundary is defined by escape becoming impossible. Light behaves as a strict traffic rule near that edge. Paths that once curve outward begin to curl inward. A signal would fail to return once it crosses the boundary. This physical edge matters because it sets the meaning of growth. Anything that crosses it adds mass. The scene holds on a dim disk with a clean inner cut. That cut is not a line. It is a steep gradient in speed and brightness. Small payoff arrives early. Growth is not a single act of falling. Growth is a process of shedding energy. Matter must lose heat and motion to move inward. The first concept takes shape as an accretion disk. An accretion disk is rotating matter that slowly spirals inward. It stays in orbit while it drifts. Friction and magnetic stresses transfer energy outward. Heat rises where motion is most extreme. The disk becomes brighter toward its inner regions. The brightness is a clue. It is also a limit. A visual anchor settles in. A pale ring glows in the darkness. The ring is not uniform. It has a brighter side where material piles up. It has a darker lane where the flow thins. The ring looks like a slow-forming sandbar in a river mouth. That sandbar is shaped by currents and by resistance. In this region, resistance is heat and radiation. A scale shift enters gently. The same physics applies from a seed no heavier than a star. The same physics applies to a giant in a galactic core. The timescale changes more than the rules change. Orbital motion near the inner disk can be measured in minutes. The build-up of mass plays out across millions of years. Another payoff arrives without fanfare. A black hole cannot simply take all nearby gas at once. The second concept is the feeding limit set by radiation. A quiet ceiling appears when light pressure balances gravity. This ceiling is often called the Eddington limit. Eddington limit means radiation pressure can halt spherical inflow. The disk is not perfectly spherical, so paths exist around the limit. The limit still shapes typical growth rates. When the inner disk shines intensely, photons scatter off electrons in the inflow. That scattering pushes outward. The push is gentle at first, it becomes strong when luminosity rises. A concrete physical detail anchors the idea. The inner disk has a bright photosphere like a fog layer. It is a surface where photons last scatter before leaving. As luminosity increases, that scattering surface inflates outward. The result is a thicker inner region. It can redirect inflow into a wind. The wind does not need a sharp edge. It begins as a gradient of density and speed. A visual anchor returns in a new form. A faint veil lifts off the disk surface. It forms a soft cone that widens with distance. The cone is made of thin gas and dust. It is not a jet. It is a slow outflow. It resembles a dry gust that lifts fine powder from a flat plane. The plane here is the disk's surface. The powder is ionized gas. The payoff is clear. Feeding and shining are linked. Faster growth tends to make stronger light. Stronger light tends to push matter away. The third concept arrives as the question of seeds. Seed mass sets the starting point for growth. A seed can form from stellar collapse. A seed can also form from direct gas collapse. The early universe favours dense gas and rapid inflow. That changes the odds for heavy seeds. A single number frames the whole story. Some black holes reach about 1 billion times the Sun's mass. That mass is like stacking 1 billion suns into one dark centre. It also resembles the mass of a small galaxy compressed into a point. Reaching that mass is hard under steady limits. It demands either a heavy seed fast feeding or both. The scene shifts outward. The disk is now a bright hub in a larger cloud. Filaments of gas connect to it like streams feeding a lake. The lake has no shoreline. Its boundary is a change in orbital order. Gas falls in. Gas also settles into rotation. Angular momentum is the gatekeeper. It keeps matter circling instead of plunging. A small payoff appears. The real problem is not attraction. The real problem is losing sideways motion. When gas has too much angular momentum, it stays far out. It forms stars or it disperses. When gas can shed angular momentum, it flows inward. In that region, turbulence acts like a slow brake. Magnetic fields act like a hidden clutch. They couple inner and outer rings. They transfer angular momentum outward. That transfer lets the inner flow move inward. A physical detail sharpens the image. The disk develops spiral density waves. These are ripples of overdensity that sweep around. They compress gas and heat it. They also provide a route for momentum transport. A new visual anchor appears. The disk looks like a dark vinyl record with faint grooves. The grooves are density waves. They glide around the centre at a different speed than the gas. They create alternating bright and dim arcs. The arcs change over time. Some fade, some sharpen. The payoff is immediate. Growth is not smooth because the supply is not smooth. Clumps arrive. Streams align and misalign. The disk responds by rearranging its layers. The scale shift continues. Near the inner regions, the flow changes within hours. In the broader region, supply changes over thousands of years. In the host galaxy, the supply changes over millions. This layered timing keeps the story calm. It also explains why black holes can shine in bursts. A limit of observation enters softly. The boundary itself cannot be imaged directly by light that crosses it. Any direct view is impossible. Only nearby light can be measured. That light is distorted by strong gravity and by scattering. Resolution is limited by distance and by intervening plasma. Models rely on inference from brightness patterns and timing. An object would produce similar signals under different geometries. That creates degeneracy in interpretation. The constraint is not ignorance. It is the nature of indirect measurement. Even so, patterns can be trusted in broad strokes. A dark central shadow can be inferred from missing light. A ring can be inferred from curved paths. A rapid flicker can be tied to compact size. These are gentle anchors rather than sharp proofs. Another payoff settles in. The key ingredients of growth are simple. A seed provides the start, a disk provides the pathway, radiation provides the debris. The details decide the outcome. When the seed is heavy, the climb is shorter. When the supply is dense and continuous, the climb is faster. When the inner region traps radiation, the break is weaker. That last idea remains for later. For now, the scene returns to the dim disk. Its inner edge is smooth. Its outer edge blends into fog. The brightness fades with radius. The flow remains ordered by rotation. Time stretches. A few minutes of orbital motion repeat endlessly. Millions of years pass in slow accumulation. The transition stays gentle. The next step is to examine what seeds exist at the start. The next step is to see how different seeds shape later growth. In the early universe, a black hole begins as a seed that is small but decisive. Seed mass sets the starting step and narrows the range of growth histories. At this distance, the first question is not brightness. The first question is how a compact centre appears at all. The region begins as a dense cloud with uneven pockets. Some pockets collapse into stars, some collapse into a single heavy core. A seed can form from the death of a very massive star. The core becomes compact. The surrounding layers fall inward. The collapse ends with a steep boundary where matter becomes extremely dense. A smooth inner region forms. Around it, infalling material creates a temporary shell that heats and thins. The physical detail is a strong gradient. Density rises sharply towards the center. Pressure rises with it. A small payoff arrives early. A seed does not need to be large to matter. A seed only needs to exist in the right place. Once present gravity organizes nearby gas into orbits. The first concept is the stellar remnant seed. It is a compact object left by core collapse. It begins with a mass in the range of a few suns. The everyday comparison is simple. It is like compressing several suns into a volume smaller than a city. The number is rounded and safe. It frames a seed as small compared with a later giant. It also frames a seed as already extreme. The scene turns slow and clear. A dark center sits inside a faint hot cocoon. The cocoon is not a surface. It is a layer of gas with a temperature gradient. The outer layer is cooler and more diffuse. The inner layer is hotter and denser. Light behaves as a restless shimmer through that layered gas. A signal would leave with its path scattered by electrons. The image stays calm. The cocoon expands and fades. The seed remains. Another payoff arrives. The first growth step is often limited by supply, not by desire. A small seed can sit in a thin environment. It grows slowly. A small seed in a thick inflow grows faster. The next concept is direct collapse. Direct collapse means a gas cloud collapses mostly as one piece. It avoids fragmenting into many stars. Fragmentation is the usual outcome when gas cools efficiently. Cooling lets clumps form. Clumps become stars. Direct collapse requires conditions that keep the cloud warm or stirred. The result is a heavier seed. A heavier seed has a shorter climb to the billion-sun scale. The visual anchor becomes distinct and new. A broad, smooth cloud narrows into a central funnel. The funnel is not sharp. It is a gentle rotating throat where streams meet. The cloud looks like warm syrup draining toward a small opening. The syrup is not sticky. The comparison is about flow and thickness. The payoff is clear. When fragmentation is delayed, mass gathers in one place. The seed begins larger. The scale shift becomes soft and wide. The funnel region spans light years. The compact seed that forms is far smaller than a planetary orbit. The time shift is just as gentle. The cloud evolves over hundreds of thousands of years. The inner collapse happens much faster. Minutes and hours matter near the final compact stage. Yet the large-scale supply takes ages to change. A third element enters without adding a new concept. It is the environment that sets the odds. In dense early regions, gas arrives along filaments. Filaments are long streams of higher density. They guide inflow toward the center. The physical detail is layering in motion. The filament has a denser spine and a softer envelope. The spine feeds the core. The envelope peels away into orbit. The scene holds on a filament that bends. It joins another. Their junction is brighter from heating. A small payoff arrives. The seed pathway leaves different scars in the surroundings. A stellar collapsed seed begins with a brief hot shell that expands. A direct collapse seed begins with a thicker, rotating inflow. The later accretion disk inherits that history. It inherits angular momentum and gas composition. The difference matters because growth depends on how easily gas settles into a disk. A disk requires rotation. It also requires a way to shed energy. The seed does not supply that. The environment supplies that. A limit of observation arrives softly. These seeds form at great distances and early times. Direct images of the forming seed are impossible. Light from the deepest region is absorbed or scattered. Resolution is limited by distance and by intervening gas. Models rely on indirect clues. Spectra and variability suggest compactness and accretion. They do not uniquely reveal the seed pathway. Several different initial masses can produce similar brightness later. This is a limitation of inference, not a failure of theory. The best statements remain order of magnitude safe. Heavy seeds make early giants easier. Light seeds require long, steady feeding or special episodes. The calm story continues with another payoff. A seed is not a guarantee. It is a starting point inside a moving river of gas. If the river is cut off, growth stalls. If the river stays open, growth proceeds. The core physical picture stays simple. A central compact mass shapes orbits. Gas settles into a rotating structure. Energy loss lets it drift inward. The scene returns to the funnel cloud. The central region becomes smoother as turbulence decays. The outer region remains lumpy. The boundary between them is a soft shear layer. It is a place where flows slide past each other. Over time, the sliding can turn into heat. That heat can delay fragmentation a bit longer. The scale shift widens one last time. A seed of a few suns can be the ancestor of a billion-sun giant. The journey spans most of cosmic history. The path begins in a quiet pocket of gas. It ends in a massive dark center at a galaxy's heart. The transition stays gentle. The next section moves closer to the disk. The next section explores how feeding limits appear when light pushes back. A growing black hole becomes brightest at the moment growth tries to accelerate. The same light that reveals accretion also resists further inflow. In that region, a thin disk forms a bright inner band and a dimmer outer skirt. The brightness rises toward a sharp inner gradient. The gas there is hotter and more ionized. Light behaves as a steady wind inside that inner glow. Photons stream outward and strike free electrons in the inflow. Each strike transfers a tiny push. A small payoff appears quickly. Growth has a built-in brake because light carries momentum. The first concept is the Eddington limit. Eddington limit is luminosity where radiation balances gravity for ionized gas. When luminosity approaches that level, outward push can match inward pull for diffuse gas. The balance is not a wall. It is a region of competing forces. The scene holds on a luminous crescent that hugs the inner disk. Above it, a translucent haze lifts from the surface. The haze is thicker closer in. It becomes thinner with height. The physical detail is a scattering layer. It acts like a soft skin around the brightest zones. The second concept is opacity. Opacity is how strongly matter blocks and scatters light. In hot, ionized gas, electrons provide a common kind of opacity. They scatter photons without destroying them. That scattering makes radiation pressure effective. The limit depends on how much opacity the gas carries. A small payoff arrives. The brake is stronger when gas is more easily pushed by light. The bright inner disk also shapes the flow by geometry. A disk radiates more strongly upward than sideways. That gives inflow a path along the midplane. The midplane remains dense. The upper layers become a lifted veil. The new primary analogy stays natural and calm. Radiation pressure resembles an updraft that keeps fine dust suspended. Gravity resembles the quiet settling of that dust back downward. When the updraft strengthens, dust stays aloft longer. When it weakens, dust sinks through still air. In this cosmic version, dust is ionized gas and scattered light is the updraft. The visual anchor deepens. The inner disk is a bright ring with a soft halo. The halo looks layered. It has a brighter underside and a dimmer outer rim. The rim is shaped by a gradient in density and temperature. The halo is not smooth everywhere. It contains faint streaks that drift and blur. A small payoff follows. The halo is a sign that some energy escapes before it can help growth. As radiation rises, the flow adapts. Gas does not stop arriving. Gas changes its route. A portion turns into a wind from the disk surface. That wind is slow near its base. It accelerates with height. The acceleration is driven by photons scattering many times. Each scattering adds a little push. The wind carries away mass and angular momentum. That removal can reduce the supply reaching the center. It can also reshape the disk. The disk becomes thicker where pressure grows. The thickness changes the radiation field. The field changes the thickness again. Another payoff arrives. The feeding limit is not only a number, it is a feedback loop between structure and light. One rounded number sets a quiet timescale for steady growth. The characteristic doubling time near the limit is about 30 million years. That span is like the interval between large shifts in Earth climate. It is short on cosmic scales. It is long compared with a single orbit near the inner disk. The scale shift becomes gentle and wide near the inner edge gas circles in minutes or hours. Over 30 million years, the central mass can grow by a large factor if fuel stays available. This contrast explains why brief flickers matter. Flickers show inner motion. Growth requires long continuity. The scene shifts outward to the supply. Filamentary gas approaches in streams. The streams meet a rotating disk. The outer disk is cooler and more clumpy. Inflow there is uneven. It arrives in patches that compress and spread. The inner disk smooths these patches into a steady glow. That smoothing is not perfect. It leaves subtle variations. Light behaves as a messenger of these changes. Variation in brightness hints at changing inflow, yet the limit remains present. As brightness increases, the scattering layer thickens. The thickening increases the effective push on upper gas. The push strengthens the wind. Another payoff arrives. A bright phase can shorten itself by clearing its own surroundings. A limit of observation enters softly. Accretion rate is not measured directly. Luminosity is observed, but luminosity depends on radiative efficiency. Efficiency depends on disk thickness and magnetic stresses. Dust and gas can absorb and reprocess light. That can hide true power. Geometry can collimate light and make it appear stronger. Several different flows can produce similar spectra. This is a limit of inference and resolution. The deepest region is smaller than direct imaging can resolve. The inner halo is also shaped by scattering. Scattering blurs the origin of photons. Even timing signals are filtered by delays in the surrounding gas. Reliable statements remain broad and cautious. High luminosity suggests high inflow or high efficiency. It does not uniquely reveal both. Another small payoff settles. The Eddington limit guides typical growth even when exact rates are uncertain. The limit also hints at pathways to exceed it. A disk can be thick enough to trap radiation. Trapped radiation escapes more slowly. Pressure can then leak outward without stopping inflow at the midplane. The scattering layer becomes a funnel-shaped envelope. The envelope directs photons away from the densest inflow. The densest inflow continues inward in shadow. The physical detail is a self-made shade. It is a region where photons struggle to pass. Light behaves as a slow diffusion there. A signal would wander by many scatterings before escaping. This sets the stage for episodes that look brighter or dimmer than expected. It also sets the stage for faster growth than a simple spherical picture allows. The visual anchor returns in a final calm form. A bright inner ring is partly wrapped in a pale cocoon. The cocoon has a clear gradient from thick to thin. The ring remains stable in shape. The cocoon breathes in thickness over long intervals. The story stays gentle. The next section moves into the disk that grows thick. The next section follows how trapped radiation changes the feeding limit without drama. A feeding limit changes character when the disk becomes thick enough to hide its own light. The inflow can continue because trapped radiation escapes too slowly to push it back. At this distance, the accretion disk no longer looks like a thin sheet. It swells into a rounded layered torus with a dim core. The inner region has a steep gradient in density. The surface is not sharp, it is a broad scattering skin where photons last change direction. The first concept is photon trapping. Photon trapping is radiation carried inward faster than it escapes. In a thin disk, photons leave quickly. Heat turns into light and streams away. In a thick flow, photons bounce through dense layers. Scattering delays their escape. The delay matters because pressure cannot act outward until light gets out. A small payoff settles early. The limit is softened when light cannot leave on time. The visual anchor holds steady. A puffed ring glows with a muted brightness. Its upper surface looks like a soft dome. Its underside looks darker and heavier. Near the center, a narrow axial chimney opens. It is not empty. It is a lower density channel. Light behaves as a preference in that geometry. Photons drift toward the easier route. They leak upward through the chimney more than through the dense walls. The second concept is the thick accretion flow. Thick flow means the disk height rivals its radius. It is not a precise boundary. It is a change in shape and transport. Gas pressure rises. Radiation pressure rises with it. The flow becomes more like a swollen envelope than a flat ring. A scale shift enters gently. Near the inner edge, conditions change over minutes. Farther out, the torus holds its shape over thousands of years. Across millions of years, repeated thick phases can build large mass. The payoff arrives in plain view. A thick flow can accept high inflow while showing only modest light. The bright output is not a direct meter of the true rate. Some energy is carried inward with trapped photons. Some energy leaves through narrow paths. Some becomes a wind from the surface. The scene moves along the torus skin. The skin is a gradient. It is denser near the midplane. It is thinner near the top. Scattering is strongest where density is highest. That creates a soft boundary between bright and dim. It also creates a sense of depth. A slow visual moment arrives. Faint ripples travel along the surface. The ripples are density waves and pressure waves. They tilt and fade. The chimney remains steady. Another payoff arrives. Geometry can protect inflow by giving light an easier escape route. In that region, a dense midplane can stay shadowed. Radiation escapes upward. The midplane feels less push. The inflow continues inward under gravity. This is not a violation of the feeding limit. It is a change in how the limit applies. The limit is derived for spherical flow. The thick disk is not spherical. Light behaves as a pattern, not a uniform glow. The primary analogy stays calm and natural. A cooling lava lake forms a dark crust. Heat remains beneath that crust longer. Steam escapes through cracks and vents. The crust is the dense disk interior. The vents are the axial chimney and surface pores. The analogy is about delayed escape, not about violence. It unlocks a simple idea. When escape is delayed, pressure acts later. The torus can keep growing while its light finds narrow exits. A rounded number gives the story a stable scale. The thick region can extend to about 100 times the event horizon radius. That span is like placing a small bead at the center of a wide ring. The bead is the horizon scale. The ring is the thick zone. The comparison keeps the distance easy to picture. Within that span, temperature and density change quickly. Gradients are steep. A small payoff follows. The inner geometry sets what part of the flow is visible. If the chimney points toward empty space, more light escapes. If the chimney is blocked by dense gas, light is reprocessed and softened. The same inflow can appear bright or faint. The same inflow can appear hot or cool. The visible spectrum depends on scattering and absorption in the skin. It depends on how photons diffuse outward. A slow scene returns to the chimney. A pale glow rises through it. The glow is not a beam. It is a concentrated leak. The edges of the chimney are fuzzy. They are shaped by shear and turbulence. The walls of the chimney shimmer as density fluctuates. Light behaves as a river in fog there. It flows along the least resistant path. It bends around denser knots. It exits in pulses as knots pass. Another payoff arrives. Short variability does not always mean small inflow changes. Variability can come from changing paths of escape. The inflow may remain steady while the visible light flickers. That is a gentle reminder about interpretation. A limit of observation enters softly. The true accretion rate cannot be measured directly. Luminosity is filtered by beaming and by obscuration. Thick flows hide their inner regions behind scattering skins. Spectra can be altered by reprocessing in cooler layers. Different combinations of rate and geometry can look similar. Timing signals can be smeared by multiple scatterings. This is a limit of inference and resolution. It is also a limit of intuition. It feels natural to link brightness to feeding. Thick flows break that link in a controlled way. reliable statements remain broad. A thick flow can allow faster mass gain than a thin disk suggests. The exact factor depends on geometry and on how much energy escapes. The scene widens outward. A dense inflow meets the outer disk. The outer disk feeds the torus in clumps. Each clump spreads into a spiral. The spiral becomes a pressure wave. The pressure wave travels inward and changes the skin thickness. The chimney brightens and dims as the wave arrives. A small payoff lands. Thick phases can come and go without changing the seed itself. The seed remains. The supply decides the state. When supply rises, the disk puffs up. When supply falls, the disk thins. This creates a natural rhythm across long eras. The scale shift is calm. Minutes of inner turbulence repeat inside thousands of years of disk shape. Those thousands repeat inside millions of years of growth. Another visual anchor moment closes the body. The torus glows like a muted ring around darkness. A dim seam marks the dense midplane. A pale plume rises through the axial channel. The plume fades into a softer halo. The halo merges with the surrounding cloud. The tone stays steady. The next section moves closer to the inner edge where orbits end. The next section follows how rotation changes the last stable path inward. Rotation quietly reshapes the last safe orbit around a black hole. Spin sets how close matter can circle before stability ends and inward drift becomes unavoidable. At this distance, the inner disk appears as a bright narrow band with a clean inner edge. That edge is not a surface. It is a transition where stable paths end and plunging paths begin. The glow strengthens toward the center. The gradient is steep in temperature and orbital speed. Light behaves as a curved traveller there. Paths bend and wrap. The first concept is spin. Spin is the black hole's angular momentum in space-time. It does not add a hard surface. It changes the geometry that orbits follow. When spin is low, the last stable orbit sits farther out. When spin is high, that orbit moves inward. A small payoff arrives early. Faster spin can raise how much energy is released before matter crosses the boundary. More released energy means brighter light per unit mass. The visual anchor holds steady as a distinct scene. A thin luminous ribbon circles the darkness. The ribbon has a sharper inner rim on one side. The opposite side looks softer and slightly wider. This asymmetry is not a preference or intention. It comes from speed and light bending. The inner rim is where motion is fastest. The fastest motion changes the light pattern. The second concept is the innermost stable orbit. Innermost stable orbit means the last circular path that remains stable. Inside it, small disturbances grow. Orbits cannot remain circular. The flow turns into a plunge. The definition is short. The picture becomes simple. The disk is a ring road around a deep center. The ring road ends at a boundary. Past that point, the path tilts inward and does not recover. A small payoff follows. The inner edge is a physical clue to spin because it sets where the brightest heating occurs. A rounded number gives scale without clutter. For a non-spinning case, the last stable orbit lies about 6 times the horizon radius. That separation is like 6 gentle ripples laid one inside another in still water. It is a small distance in absolute terms. It is large in effect. Moving that edge inward changes temperature and brightness strongly. The scene moves closer to the inner rim. The disk surface becomes smoother. Turbulence is present, but it blends into a steady flow. The glow is not uniform. It flickers in faint patches. These patches drift with the rotation. They smear into arcs. Another payoff arrives. The strongest light often comes from a narrow zone because most energy is released near the end of stable orbits. Spin shifts that zone. The third concept arrives as a subtle consequence of rotation. The space near the black hole is dragged in the direction of spin. Frame dragging, a space-time pulled around by rotation. The definition stays short. The effect becomes visual. The flow's inner layers are guided into a preferred swirl. Orbits that match the spin can remain stable closer in. Orbits that oppose the spin become unstable farther out. This is not a choice. It is geometry. Light behaves as a curved thread within that geometry. A signal would follow a path that is bent and delayed. The ribbon of light appears thicker where bending piles up paths. A new everyday analogy carries the idea without human traces. In a tidal pool, a whirlpool tightens when the tide accelerates through a narrow gap. The outer water still circles broadly. The inner circle shrinks and spins faster. The tightening does not require a wall. It comes from flow and rotation. In the disk, spin-bin plays the role of the accelerating tide. The innermost stable orbit plays the role of the shrinking inner circle. The payoff is immediate. A tighter inner circle means more energy can be shed before the plunge. The scene widens outward for a gentle scale shift. Near the inner rim, conditions change over minutes. Heat rises and falls with small variations in inflow. Farther out, the disk changes over thousands of years. Over millions of years, sustained high spin can keep the inner edge close. That allows repeated bright episodes to extract more energy from each unit of mass. This does not guarantee faster mass gain. It changes the light per mass. It also changes the feedback. A brighter output can drive stronger scattering and winds. Another payoff arrives. Spin can both help radiate energy and strengthen the brake that radiation applies. The physical detail becomes more concrete. Close to the inner rim shear is extreme. Neighbouring rings move at different speeds. That shear heats the gas. It also amplifies magnetic fields. The disk develops a layered structure. A dense mid-plane carries most of the mass. A hotter skin carries much of the light. Between them lies a region of strong gradients. Temperature changes quickly with height. Ionization changes with it. The light emerging from this layered region carries imprints of motion. Some photons reflect off the disk's surface, some scatter through hot plasma, some are bent back toward the disk and strike it again. The ribbon glow becomes a looped pattern, like a soft halo hugging the inner edge. A small payoff follows. Spin is encoded in where the inner edge sits, and in how light is bent around it. A limit of observation enters softly. Spin is not seen directly. The inner edge is not traced by a visible line. It is inferred from spectra and timing. Those inferences rely on models of disk thickness and radiative transfer. A thick disk can hide the true inner edge behind scattering layers. Inclination can mimic some spin signatures. Magnetic stress can extend dissipation inside the nominal stable orbit. This creates degeneracy in interpretation. Resolution limits keep the deepest region unresolved. The safest conclusions stay broad. High spin is consistent with a smaller inferred inner edge. Low spin is consistent with a larger one. Exact values depend on assumptions that cannot be fully checked. Another payoff settles. Even with uncertainty, the spin story clarifies why some systems shine more efficiently than others. It also clarifies why the same inflow can look different across time. When the disk puffs up, scattering changes and signatures blur. When the disk thins, signatures sharpen. The scene returns to the luminous ribbon. The inner rim remains clean in overall shape. Small, bright knots drift along it. Each knot fades and is replaced. The darkness at the centre remains featureless. The boundary remains defined by escape, not by texture. The scale shift expands one last time. The inner rim is only a few horizon radii from the centre. The host galaxy spans tens of thousands of light years. Between these scales, inflow must travel through many regimes. Each regime can tilt and twist the disk. The transition remains gentle. The next section follows what happens when supply arrives misaligned. The next section explores how disks can warp, tear, and resettle without noise. A disk stays calm only when incoming gas arrives in the same plane. Misaligned supply can bend the disk and briefly split it into drifting layers. In that region, the inflow carries its own direction of rotation. That direction is not guaranteed to match the inner disk. The mismatch creates a slow twist. A warp forms. The disk is no longer a single flat ring. It becomes a surface with a changing tilt as radius increases. The physical detail is a gradient in orientation. The inner rings point one way. The outer rings point another. Between them lies a shear zone where neighbouring layers slide past. Light behaves as a tracer of this geometry. Brightness concentrates where the surface is most compressed. Shadows appear where a raised ring blocks illumination. A small payoff arrives early. Growth can continue through disorder because the disk can realign itself. The first concept is a warped disk. Warped disk means the disk plane changes with radius. The definition is short. The picture is slow and clear. A shallow bowl shape develops in the disk surface. The bowl is not symmetric. One side is lifted. One side is lowered. The lift changes how photons escape. It also changes where the disk is heated. The visual anchor becomes distinct and new. A luminous spiral ribbon crosses itself like a gently twisted sash. Along the twist, a dim lane forms where one layer shades another. The lane stays in place for a while. It drifts as the warp precesses. The second concept is precession. Precession is slow rotation of an orbit's tilt direction. In a warped disk, rings precess at different rates. Inner rings respond more strongly to the central geometry. Outer rings respond more to incoming supply. The mismatch makes the warp travel like a wave. A small payoff follows. The warp is not static. It moves. It can carry angular momentum and help the disk settle. The third concept is alignment. Alignment is the process of bringing inner and outer planes together. It happens through viscosity and through magnetic stresses. It also happens through shocks where layers intersect. When misaligned streams fall onto the disk, they can form a tilted outer ring. That ring tries to share its direction with the inner rings. Friction turns that disagreement into heat. Heat changes thickness. Thickness changes viscosity. The disk gradually chooses one plane. The analogy stays unique and calm. A stack of thin ice sheets on a slow-moving river drifts at slightly different angles. Where edges meet, they rub and melt. The meltwater lets the stack settle into a smoother shape. The ice sheets are disk layers. The rubbing is shear. The melt is dissipation. The payoff is immediate. Dissipation is the quiet tool that resolves misalignment into a new stable flow. A rounded number sets the timescale without strain. The warp can persist for about 10,000 years. That span is like the lifetime of a small island of sand in a changing sea. It is long compared with inner orbits. It is short compared with galaxy evolution. The scale shift becomes gentle. Inner rings complete cycles in minutes or hours. The warp pattern drifts over centuries. The overall alignment takes thousands of years. Over millions of years, repeated misaligned episodes can change the average spin direction. Another payoff arrives. Chaotic feeding can keep spin from reaching extreme values. When inflow arrives from changing directions, the black hole can gain mass without always gaining a line spin. This reduces radiative efficiency at times. It can also soften radiation feedback. The physical detail returns in a new form. At the interface between tilted rings, the disk can tear into discrete planes. The tear is not a break into empty space. It is a sharp change in tilt over a narrow radial range. Two planes intersect. At the intersection, gas collides. Collisions create a hot line. That line cools as it spreads. The brightness there can pulse as new streams arrive. A slow visual moment arrives. Two faint rings cross like overlapping halos. Where they overlap, a narrow bright arc forms. The arc slides around the centre as precession continues. The rest of the disk remains dimmer and smoother. A small payoff follows. Collisions at the overlap remove angular momentum quickly. That can drive a brief surge of inward flow. The surge is not a burst of violence. It is a short phase of efficient inward drift. The disk then relaxes. It becomes smoother again. Light behaves as a soft messenger. It shows these changes through shifting shadows and moving bright arcs. A limit of observation enters softly. Warps and tears happen on scales far too small to image directly at most distances. Their signatures are indirect. Spectral lines can broaden and skew, but many geometries can do that. Brightness variations can suggest precession, but variability can also come from turbulence. Dust and gas can obscure the outer rings. Scattering can smear the timing. Models depend on assumptions about viscosity and magnetic stress. Those assumptions are uncertain in detail. This is a limit of measurement and of theory calibration. The safest statements remain qualitative. Misalignment produces warps. Warps can create shadows. Dissipation tends to align flows over time. Another payoff settles. Even with uncertainty, warped disks explain why some systems show changing illumination patterns without large changes in total supply. A tilted ring can shade part of the disk. The shaded region cools. Cooling changes opacity. Opacity changes where light emerges. The system can look different while feeding remains similar. The scene widens outward to the supply lines. Filaments deliver gas with changing angles. Some streams arrive gently. Some arrive as clumps. Clumps spread into arcs. Arcs thicken into rings. Rings lean and then settle. The warp wave travels inward. It fades as alignment proceeds. The disk becomes flatter. The inner edge remains defined by stable orbits. The outer edge remains diffuse and clumpy. The scale shift expands one last time. A misalignment seeded by a single inflow episode can persist for 10,000 years. Over 1 billion years, many such episodes can occur. Their cumulative effect can shape how efficiently mass turns into light. The transition stays gentle. The next section moves to a different path of growth. The next section follows mergers that add mass in quiet steps. Some growth happens without steady feeding and without bright disks. Mergers add mass in discrete steps and reshape the surrounding flow afterward. At this distance, two dark centers share the same broad gas reservoir. Each has its own small disk. Each disk has its own inner glow and scattering skin. Farther out, their gravity fields overlap. The overlap creates a slow pattern of tides. Gas forms elongated streams that point toward each center. The physical detail is a changing saddle of gravity. Between the two centers, there is a region where pull balances. That region is not stable. It shifts as the pair orbits. A small payoff arrives early. A merger bypasses the usual feeding limit because mass is delivered as a compact object. The first concept is a binary black hole. Binary black hole means two black holes bound in orbit. The definition is short. The picture is gentle. Two invisible centers circle a common point. Their disks are faint lamps in a large fog. Light behaves as a curved path around each center. It also bends through the combined potential. The visual anchor becomes distinct and new. A pair of dim rings revolve in a shared envelope. Between them, a thin bridge of gas stretches and thins. The bridge brightens where it is compressed. The bridge dims where it is torn into filaments. The second concept is in spiral. In spiral is an orbit that shrinks with time. The shrink can be driven by interaction with surrounding gas. It can also be driven by gravitational waves. Gravitational waves are ripples in space-time that carry energy away. The definition remains brief. The effect becomes calm. As energy leaves, the orbit tightens. Periods shorten. Tides strengthen. The surrounding gas responds. It can form a cavity around the binary. That cavity is a low-density gap. Its edge is a steep gradient in density and temperature. Another payoff arrives. The cavity edge becomes a new kind of feeding gate. Gas piles up at the rim of the film. It waits for streams to cross the gas. The streams fall inward in pulses. Each pulse feeds the small disks briefly. The scene moves along the cavity rim. The rim is not circular. It is slightly lopsided. It has a brighter sector where streams strike. It has a quieter sector where gas is thinner. In that region, the orbital motion of the binary drags the rim pattern around. The rim looks like a soft oval ring with a moving bright notch. The analogy stays unique and calm. Two eddies in a slow river draw water into a shared shallow basin. The basin's edge gathers floating leaves. Leaves cross the basin only in narrow channels. The eddies are the black holes. The basin is the cavity. The leaves are gas parcels drifting with angular momentum. The payoff is immediate. Even before merger, the binary can regulate feeding by shaping where gas can cross. A single rounded number sets the scale shift gently. Near the end, the final orbit can tighten to a period of about a minute. That minute is like the time it takes a candle flame to waver and settle. It is short compared with earlier orbital periods. It is tiny compared with the age of galaxies. The scale shift becomes clear. Millions of years can pass during the Earlian spiral. The last minutes pass with rapid tightening. The visual anchor shifts closer without haste. The two dim rings begin to overlap in projection. Their inner rims blur as velocities rise. The cavity becomes smaller. The edge becomes sharper. Light behaves as a more extreme curve. Paths loop around the pair before escaping. A signal would be delayed by changing gravitational fields. Another payoff arrives. The final stage is not powered by light. It is powered by geometry and by space-time radiation. The gas may become secondary. The merger completes when horizons join into one. The joining leaves a single remnant with a new spin and a new mass. Some energy is carried away by gravitational waves. That energy is a small fraction of the total mass energy. The remnant can also receive a recoil. The recoil comes from asymmetry in wave emission. The recoil can shift the remnant relative to the gas. That shift matters for later feeding. The physical detail becomes tangible again. After merger, a disturbed disk can form. The cavity can refill. Shocks can propagate through the surrounding gas. The refilling is not instantaneous. It is shaped by angular momentum barriers and by cooling. A slow visual moment arrives. The shared envelope settles into a single broad disk. A bright arc travels outward like a ring wave in a pond. The arc is a compression front. It fades as it spreads. Behind it, the density gradient softens. The payoff follows. Mergers can reset the central environment and create a new episode of disk building. A limit of observation enters softly. The merger itself is difficult to observe in light. If gas is sparse, there is little electromagnetic signature. If gas is thick scattering, an obscuration can hide the inner changes. Timing of light variations can be ambiguous. Similar flickers can be produced by turbulence. Spectral shifts can be produced by winds. Direct imaging of the binary is beyond resolution for most distances. Inference relies on modelling and on rare coincident signals. This is a limitation of measurement, not a lack of physical pathways. The safest statements remain broad. Mergers add mass in steps. Mergers reshape spin and can create cavities and refilling waves. Another payoff settles. Mergers help build large masses when steady feeding alone is too slow. They also mix growth channels. A black hole can grow by accretion for long eras. It can then gain a large fraction of mass in one merger. The combined path can reach giant scales within cosmic time. The scene widens outward to the host region. Multiple dark centers can form in the same dense environment. Over time, their orbits sink through interactions with gas and stars. Their mergers become part of the long arc of assembly. The scale shift expands gently. A 1-minute final orbit sits inside a process that unfolds across billions of years. The environment changes while the geometry remains strict. The darkness remains defined by boundaries, not by surfaces. The transition stays calm. The next section turns back to light and outflow. The next section follows how winds and jets can clear supply and set a self-limiting pace. A bright disk often announces its own limits by sending part of its energy outward. Outflows can clear the neighbourhood and regulate how long feeding stays steady. In that region, the inner disk glows with a concentrated heat. Above the disk, a hot skin forms. It is thinner than the midplane and more ionized. The boundary between skin and midplane is a gradient in density and temperature. Light behaves as both heater and pusher there. Photons scatter in the skin. The scattering transfers momentum outward. Gas begins to lift away from the surface. A small payoff arrives early. The same process that makes a disk luminous can also remove the fuel that keeps it luminous. The first concept is a disk wind. Disk wind is gas lifted from the disk by forces. Those forces can be radiation pressure and thermal pressure. The definition is short and gentle. The picture is clear. A faint veil rises above the bright ring. The veil is not uniform. It has streaks where density is higher. It has holes where gas is thinner. The wind begins slow and becomes faster with height. The physical detail is layering. Close to the disk, the flow is dense and opaque. Farther out, the flow becomes transparent and diffuse. A visual anchor becomes distinct and new. A wide hollow cone of mist expands above the disk. The cone is brighter along its rim where scattering is strongest. The interior is dimmer and clearer. The rim undulates like a slow breathing edge. The second concept is a jet. Jet is a narrow, fast outflow along the rotation axis. It is not made by ordinary gas pressure alone. It is shaped by magnetic fields and by rotation. The definition stays brief. The effect becomes visual without human references. A thin column forms inside the hollow cone. The column is straighter and more collimated. Around it the wind continues as a wider veil. The column and the veil work together. The column can carve a channel. The veil can carry mass away from the disk surface. Another payoff arrives. A jet can reduce supply by stirring and heating gas farther out. It can also allow some light and energy to escape without pushing on the dense midplane. This makes feedback complex but still orderly. A single rounded number gives scale. The outflow can inflate cavities tens of thousands of light years across. That span is like the width of a large galaxy's visible disk. The comparison keeps the size tangible. The scale shift becomes gentle. The jet begins near the horizon scale. It reaches far beyond the bright disk. It can extend into the host region over millions of years. Meanwhile, the inner disk flickers on timescales of hours. The same engine spans both rhythms. The scene moves along the cone wall. The wall is a scattering surface. Photons strike it and diffuse outward. The wall has a smooth pressure gradient. It also has embedded clumps. Clumps cast soft shadows into the interior. Light behaves as a pattern of bright bands and dim lanes. A signal would be delayed by repeated scattering in the denser parts. A small payoff follows. Shadows in the wind can reveal the wind's structure even when the disk itself is hidden. The analogy stays unique and calm. Steam rising from a warm lake forms a low fog. A steady breeze shapes the fog into a tilted sheet. Thin gaps open and close as the breeze shifts. The fog is the disk wind. The breeze is radiation pressure and thermal expansion. The lake is the hot disk surface. The comparison is about lifting and shaping rather than force. It unlocks a simple idea. Outflows are not separate events. Outflows are a natural continuation of the disk atmosphere. The scene widens outward to the host gas. The wind and jet deposit energy into surrounding material. Gas can be pushed into shells. A shell is a thin, dense layer that expands. Behind the shell is a lower density cavity. The cavity is a physical memory of feedback. Its edge is a sharp gradient in density. The shell can cool as it expands. Cooling can make it thinner. It can also make it fragment into knots. Another payoff arrives. Clearing gas does not always end growth permanently. It can delay growth and then allow a later return when new gas arrives. The system can cycle between bright and quiet phases. The limit of observation enters softly. Outflows are inferred from broadened lines and from large-scale emission patterns. Those patterns can be shaped by viewing angle and by obscuration. A wide wind-seen edge on can mimic a thicker disk. A jet seen off axis can appear faint. The true kinetic power is not measured directly. It is estimated from how cavities and shells respond. That response depends on gas density and cooling. Those are uncertain in distant systems. Resolution limits blur the boundary between wind and ambient medium. This is a limit of measurement and modelling. It encourages order of magnitude statements rather than precise totals. Another payoff settles. Even with the uncertainties, outflows explain a common balance. When feeding increases, light and pressure rise. When pressure rises, winds strengthen. When wind strengthens, supply near the centre drops. This creates a self-regulating pace. It also helps connect black hole growth to host conditions. The scene returns to the hollow cone. The cone expands and becomes more transparent with distance. The inner column remains narrow. It maintains a straight line where magnetic structure holds it. The outer veil becomes mottled. It carries away dust and plasma. It also imprints gentle absorption on the light escaping from the disk. The scale shift widens one last time. The disk atmosphere changes in days. The cavity grows over millions of years. Across 1 billion years, repeated cavities and shells can reshape the central region of a galaxy. The transition remains soft. The next section moves toward the host itself. The next section follows how feedback links central growth to the wider stellar bulge and gas reservoir. A black hole grows inside a larger system that can either feed it or starve it. Feedback links the small central region to the wider reservoir through pressure heating and motion. In that region, the outflow from the inner disk meets surrounding gas. The meeting produces a boundary. It is a thin shell where density rises sharply. Inside the shell is a lower density cavity. Outside the shell is cooler gas that has not yet been disturbed. The boundary is not perfectly smooth. It contains ripples and knots. Light behaves as a soft lamp within that structure. The brightest glow traces the compressed rim. The dimmer glow fills the cavity. A small payoff arrives early. The host is not a passive container. The host becomes part of the growth mechanism. The first concept is feedback. Feedback is energy from accretion changing the surrounding gas supply. The definition is short. The picture is calm. A steady push from radiation and winds gently inflates a bubble. The bubble expands into the surrounding medium. As it expands, it cools and slows. It also sweeps gas into a shell. The shell can become a barrier to inflow. It can also become a trigger for new cooling and fragmentation farther out. The visual anchor becomes distinct and new. A glowing, nearly spherical bubble sits within a thicker band of gas. The band is a ring in projection. Its inner edge is bright. Its outer edge is softer. The ring drifts outward over time. The second concept is a cooling time. Cooling time is how long hot gas takes to lose heat. Hot gas inside the cavity is thin. Thin gas cools slowly. Dense gas in the shell cools faster. This difference matters because it sets how long the cavity stays pressurized. A small payoff follows. Feedback is strongest when heated gas stays hot long enough to keep pushing. The shell continues to move outwards while the cavity remains overpressured. The shell thickness changes with radius. It becomes thinner as it expands. It also becomes clumpier as cooling sets in. A third element enters without adding a new concept. The gravitational potential of the host tries to pull gas back in. Some gas rebounds and returns. Some gas escapes to larger scales. The balance between push and pull sets the long-term supply. A rounded number sets a clear scale. The central region of strong influence can be about 1,000 light-years across. That span is like a small neighborhood inside a giant city. It is tiny compared with a full galaxy. It is enormous compared with the inner disk. The scale shift becomes gentle. Near the horizon, changes occur in minutes. In the inner 1,000 light-years, changes unfold over millions of years. Across a galaxy, changes unfold over 1 billion years. The same feedback event can leave marks at all these scales. Another payoff arrives. The central black hole can regulate its own fuel by heating and clearing gas only within a limited zone. Gas beyond that zone can remain cold and dense. It can later drift inward again. The system can cycle. It can also reach a steady state where inflow and outflow balance. The analogy stays unique and calm. A warm spring under a shallow pond creates a slow circulation. Warm water rises and spreads. Cooler water sinks and returns. The circulation can keep leaves from gathering at the center. It can also gather leaves into a ring at the edge. The spring is the energy source. The pond is the central galaxy gas. The ring of leaves is the swept-up shell. The payoff is immediate. Feedback can both clear a center and build a denser rim. The scene moves along the shell. The shell has a sharp inner face where pressure is highest. It has a softer outer face where it mixes with ambient gas. The inner face can show a bright rim from compression. The outer face can show wisps where instabilities grow. These instabilities are not dramatic. They are slow fingers of density that rise and fall. The cavity gas flows around them. Light behaves as a gentle gradient across the bubble. It is brighter near the center when the source is active. It fades when activity wanes. Another payoff arrives. A short active phase can create a long-lived shell because expansion continues after the source dims. This is a memory effect. The host stores energy in bulk motion. It releases it slowly. Over time, the shell can stall. It can then break into fragments that drift. Some fragments fall back. This fallback can restart feeding. A limit of observation enters softly. The relation between central mass and host properties is inferred from integrated light and gas dynamics. Those measurements average over many processes. Dust and projection can hide true geometry. Gas phases can be difficult to separate. Hot cavities are faint in many wavelengths. Cooling shells can mimic rings produced by unrelated dynamics. Timescales are long, so snapshots capture different moments in a cycle. This makes causality hard to prove. Models must assume typical duty cycles and efficiencies. This is a limit of inference and temporal coverage. Even so, broad patterns remain robust. Strong feedback correlates with lower central gas density. Weak feedback correlates with more continuous inflow. Another payoff settles. Feedback explains why growth is often episodic. A black hole shines and pushes. The push reduces supply. The system quiets. Supply returns through cooling and inflow. The cycle repeats. The cycle also shapes the host bulge. Gas can be prevented from forming dense central concentrations. Stellar motions can heat gas as well. The central region can become more stable against runaway inflow. The story stays calm and structural. The bubble continues to expand. Its rim becomes patchy. The cavity becomes more transparent. At this distance, the host appears as a broad rotating disk, or a spheroidal bulge embedded in a larger halo of gas. The central bubble is only a small feature, yet it influences where cold gas can settle. It influences where future inflow streams can connect. The scale shift expands one last time. A bubble grows over a few million years. Over 1 billion years, many bubbles can form and fade. Their combined effect can change the average supply and the average growth rate. The transition remains gentle. The next section moves to the hardest puzzle of timing. The next section follows how very early giants appear and what conditions allow rapid assembly without tension. The early universe allows rapid growth because it delivers fuel in dense, persistent streams. The fastest paths combine heavy seeds with thick, self-shielding inflow that softens the usual light barrier. In that region, the background is younger and denser. Gas is more abundant in the centers of forming galaxies. Cooling can be efficient, but fragmentation is not always immediate. Filaments feed the core like long braided strands. The physical detail is a layered inflow. Each filament has a denser spine and a softer envelope. The spine stays coherent longer. The envelope peels into orbit and forms a disk. Light behaves as a filtered glow through these layers. In the densest lanes, photons scatter many times before escaping. A small payoff arrives early. Early giants do not require exotic rules. They require a rare alignment of supply and structure. The first concept is cold flow accretion. Cold flow accretion is filament gas feeding a galaxy without strong heating. The definition is short. The picture is calm. Dark filaments converge toward a brighter central region. Their edges shimmer faintly where gas compresses. Their centers remain darker and denser. When the central region gains mass, its gravity captures the streams more firmly. The streams narrow and speed up. The second concept is a duty cycle. Duty cycle is the fraction of time a black hole accretes actively. This matters because growth is exponential under steady limits. Short gaps reduce final mass. Long active stretches make giants possible. In the early universe, the duty cycle can be high when supply is continuous. A small payoff follows. Even a moderate inflow rate can build a huge mass if it persists without long interruptions. The visual anchor becomes distinct and new. A central disk sits at the junction of several filaments. The disk is not perfectly flat. It is thick near the centre and thinner outside. Above it, a faint cocoon of scattering gas forms a soft bowl. The cocoon is brightest along a curved rim. Within the rim, a dim channel opens along the axis. Light behaves as a slow diffusion within the cocoon. It escapes more easily through the channel. The channel becomes a gentle lighthouse path without a beam. The unique analogy stays calm. A desert delta forms where several dry riverbeds meet after a rare season of steady rain. Water runs along the deepest channels. It pools in a central basin. The basin overflows through one low pass. The channels are filaments. The basin is the central disk and thick flow. The low pass is the axial escape route for radiation. The payoff is immediate. A stable supply network can keep the center fed while letting energy leak away in preferred directions. One rounded number frames the timing challenge. Some billion mass black holes appear within about 1 billion years after the first stars. That interval is like the time between slow reshaping of continents. It is short compared with the age of the universe. It is long compared with the minutes near the inner disk. The scale shift becomes gentle. Inner orbits cycle in hours. The central disk reorganizes over thousands of years. The host region assembles over tens of millions of years, yet the whole rise to giant mass must fit inside 1 billion years. That constraint is the quiet pressure behind early growth scenarios. Another payoff arrives. Heavy seeds shorten the climb and reduce the need for extreme duty cycles. A seed formed by direct collapse can start much larger than a stellar remnant. A thick disk can then accept high inflow while appearing only moderately luminous. The usual light barrier is softened by trapping and geometry. The disk becomes a swollen torus with a scattering skin. The skin creates a gradient in opacity and temperature. The midplane stays dense and shadowed. Light escapes upward. In that region, radiation pressure acts mostly on the low-density skin. It does not halt the densest inflow immediately. A calm visual moment arrives. The thick disk shows faint concentric layers like soft bands in smoke. The bands drift inward. They merge and smooth out. The axial channel remains clearer. Its rim glows where photons last scatter. The glow pulses as dense clumps pass beneath. Another payoff follows. Brightness can underestimate true feeding when photons are trapped and redirected. This helps reconcile rapid growth with modest observed luminosity in some cases. It also explains why early giants can be found as very luminous quasars when geometry favors escape. The same engine can look different depending on orientation and obscuration. A limit of observation enters softly. The earliest epochs are distant and hard to measure. Spectra are red-shifted and filtered by intervening gas. Dust can hide central regions. The seed mass is not observed directly. It is inferred from later luminosity and line widths. Those inferences depend on assumptions about geometry and radiative efficiency. Duty cycle is inferred statistically. Individual histories remain unknown. Resolution limits prevent direct views of filaments on the smallest feeding scales. This is a limit of data and of temporal sampling. Many different growth paths can fit the same observed brightness at one moment. Still, broad constraints remain meaningful. The universe is young at those times. Sustained feeding is required. Another payoff settles. The early growth puzzle is less about a single trick and more about avoiding long, quiet gaps. Filaments provide continuity. Dense environments provide large reservoirs. Thick flows provide a way to accept inflow without immediate self-regulation. Mergers can add discrete steps. Together, these pieces can build giants without breaking basic physics. The scene widens to a larger view of the forming galaxy. The filaments extend outward like faint threads into the cosmic web. The central region glows softly. The outflow cavities are smaller because the environment is dense. Pressure is quickly confined. The energy couples efficiently to nearby gas. That can regulate the host while still allowing feeding through protected lanes. The scale shift expands one last time. A filament junction spans tens of thousands of light years. The inner disk spans a region smaller than a solar system. Across 1 billion years, these scales remain linked by gravity cooling and transport. The transition remains gentle. The next section moves from early assembly to later consequences. The next section follows how growth histories leave signatures in shadows rings and the bending of light near the edge. A black hole's growth history leaves traces in the light that skirts its edge. The shape of that light depends on bending shadow and the layered disk that surrounds the darkness. At this distance, the central region is a bright ring around a dark interior. The ring is not a perfect circle in appearance. One side looks brighter and narrower. The other looks softer and wider. The physical detail is a sharp inner rim and a diffuse outer skirt. The rim marks where the hottest material orbits. The skirt marks cooler layers farther out. Light behaves as a curved path that can loop and return. Some photons skim close to the dark boundary. They bend and emerge with altered directions. A small payoff arrives early. The visible ring is not a picture of the horizon. It is a picture of the disk and of curved space-time shaping light. The first concept is gravitational lensing. Gravitational lensing is bending of light by gravity. The definition is short. The effect becomes a calm image. The far side of the disk can be seen above the near side because light curves around the center. A faint arc appears above the main ring. It is a secondary image made by bent paths. The arc is dimmer. It is also thinner. It sits like a pale eyebrow above the bright band. The visual anchor becomes distinct and new. A dark hollow sits inside a glowing annulus. Above the annulus, a second ghost ring flickers faintly. The ghost ring is not steady in brightness. It brightens where the disk surface is most luminous. It dims where the disk is shaded by its own thickness. The second concept is the photon ring. Photon ring is light that nearly circles before escaping. The definition stays brief. The picture is gentle. Some photons take a long route. They skim the region where light can orbit briefly. They exit after one or more near loops. These paths concentrate into a narrow feature. That feature is sensitive to the central geometry. It is also sensitive to scattering that blurs the image. A small payoff follows. The photon ring is a narrow ruler for space-time, but it is easily softened by plasma. The scene moves closer to the bright rim. The rim shows texture. It is not a solid boundary. It is a temperature gradient across the disk surface. Hotter patches shine more. Cooler patches shine less. These patches drift with orbital motion. Their motion is fast near the inner rim. It is slower farther out. The scale shift becomes gentle. The inner rim evolves in minutes. The outer skirt evolves over years. Yet the overall ring structure can persist over much longer intervals. The third concept is shadow. Shadow is the dark region created by captured light paths. The definition is short. The picture is calm. Light that enters certain angles cannot escape. Those directions map into a dark interior in the image. The shadow edge is not infinitely sharp. It is softened by scattering and by finite resolution. Still it forms a clear boundary between bright and dark. Another payoff arrives. The shadow size is set more by geometry than by disk brightness, so it can remain stable while the ring flickers. A rounded number provides a quiet scale. The shadow diameter is about 5 times the horizon radius. That span is like a small coin held close against a bright lamp. The lamplight spills around it and creates a crisp outline. The coin is the shadow. The lamp is the disk. The comparison keeps the geometry easy without invoking human tools. The analogy stays unique and calm. A lantern behind a thin curtain makes a bright halo. A small knot in the fabric blocks light and creates a dark spot. The knot does not glow. The halo does. The halo shape depends on folds in the fabric. The knot spot depends on where light can pass. The disk is the curtain. The knot is the capture region. The payoff is immediate. Observed structure is a blend of intrinsic emission and how paths are permitted. The scene widens to include the disk atmosphere. A scattering skin rises above the disk. The skin has a density gradient with height. Photons leaving the disk pass through it. Some scatter and change direction. This scattering can fill in the shadow slightly. It can also smear the photon ring. The brightest band can appear thicker than it truly is. A small payoff follows. A thicker plasma layer can hide fine space-time signatures even when the gross ring remains visible. The limit of observation enters softly. Imaging at horizon scales demands extreme angular resolution. Most systems are too distant to resolve. Even in nearby cases, scattering by plasma distorts the image. Emission is not uniform. It depends on magnetic fields and heating that are hard to model. Different plasma prescriptions can change the ring width and brightness. This creates uncertainty in interpreting detailed features. The photon ring is especially fragile. It can be blurred below detectability. The shadow size is more robust but still affected by resolution and calibration. This is a limit of measurement and of modelling. It encourages careful order of magnitude conclusions rather than fine claims. Another payoff settles. Even with limits, ring and shadow features provide a way to connect growth to structure. A thin disk tends to make a sharper, brighter crescent. A thick disk tends to make a wider glow and stronger self-shadowing. A high spin tends to move the brightest zone inward and strengthen asymmetry. A misaligned disk can create alternating bright and dim sectors through changing illumination. These are not unique signatures, but they are consistent patterns. The scene returns to the ghost arc above the ring. The arc brightens briefly as a hot patch passes on the far side. It fades as the patch moves. The main ring maintains a stable inner boundary while its brightness ripples. The darkness remains quiet and featureless. The scale shift widens one last time. A minute of orbital motion leaves an imprint in brightness patterns. A million years of feeding history sets the average disk thickness and magnetic structure. A billion years of mergers and inflow sets the mass and spins that shape the ring's geometry. The transition remains gentle. The next section moves farther out again to the long record of growth. The next section follows how populations of black holes reveal typical duty cycles and typical limits across cosmic time. A population of black holes reveals growth through statistics rather than through individual stories. The distribution of masses and brightness levels encodes typical duty cycles and typical limits. In that region, galaxies host quiet centers most of the time. Only a fraction are bright at any moment. This fraction is not random. It reflects how often gas reaches the inner disk and how long it stays. The physical detail is a layered environment. Cold gas clouds drift in the host. Warmer diffuse gas fills the volume between. Hot cavities persist after active phases. These layers control when a central disk can form and remain stable. Light behaves as a beacon that turns on and off across the population. Some sources shine steadily for long intervals. Others flare briefly and fade. A small payoff arrives early. A single snapshot of the sky can still reveal long histories when many objects are counted together. The first concept is a luminosity function. Luminosity function is the number of sources at each brightness. The definition is short. The picture becomes calm. A curve rises at faint levels and falls at bright levels. The bright end is rare. The faint end is common. The shape changes with cosmic time. When the universe is younger, bright sources are more common relative to today. When the universe is older, bright sources become rarer. The visual anchor becomes distinct and new. A vast field of galaxies sits in darkness with occasional soft beacons. The beacons are not clustered randomly. They appear more often in denser regions. Some beacons are surrounded by faint halos of glowing gas. Some are surrounded by cavities and shells. The second concept is a duty cycle. Duty cycle is the fraction of time a source is active. This section returns to the same term but uses it in a population sense. A high duty cycle means many sources are on at once. A low duty cycle means most are off. The duty cycle can be inferred by comparing how many galaxies host luminous centers to how many exist in total. It can also be inferred from how much total light is produced across time. Another payoff arrives. Counting active fractions provides a handle on growth without tracking each source continuously. A single rounded number frames the rarity of the brightest objects. Only about 1 in a million galaxies hosts a very bright quasar at a given time. That rarity is like finding one bright lighthouse along a coastline that spans a continent. The comparison keeps it gentle and clear. The scale shift becomes calm. The rare bright phase can last millions of years. The host galaxy persists for billions of years. The central engine changes on days. Population statistics connect these scales. A bright phase adds a substantial fraction of total growth. Quiet phases add little. Another payoff follows. Most mass is gained during relatively brief active periods, even if those periods are rare. The scene moves inward within a typical host. In quiet phases, gas at the center is scarce or hot. The density gradient is shallow. A stable cold disk does not reach the inner region. The shadowed midplane is absent or thin. In active phases, cold inflow deepens the gradient. A disk forms. Its inner rim brightens. A wind may rise and carve a cavity. The host then returns towards quiet. This cycle can repeat. The analogy stays unique and calm. A landscape that receives rain in seasons grows in bursts. Streams carve channels during wet months. During dry months, the channels remain as faint scars. Growth of vegetation happens mostly during the wet intervals. The wet seasons are luminous phases. The channels are cavities and shells. The dry seasons are quiescent phases. The payoff is immediate. The host retains memory of activity even when the center dims and those memories shape the next inflow. The scene widens to cosmic time. Early on, dense environments and abundant gas raise the active fraction. Later gas becomes more settled and less available. Mergers become less frequent. Feedback has had more time to heat and redistribute gas. The luminosity function shifts. The bright tail shortens. The faint population grows. Another payoff arrives. The decline of bright quasars over time is a natural result of changing supply and stronger regulation, not a sudden rule change. A limit of observation enters softly. Surveys miss obscured sources. Dust can hide active centers. Orientation can reduce apparent brightness. Variability can move sources between bins. Estimating masses requires line widths and assumptions about geometry. Those assumptions can bias distributions. At high distances, selection favors the brightest objects. Faint populations are incomplete. This is a limit of sampling and inference. It means duty cycle estimates carry uncertainty. Still, multiple methods converge on broad ranges. The bright phase is rare. The total integrated light implies substantial accreted mass over cosmic history. Another payoff settles. Even imperfect data supports a consistent picture. Growth is bursty. The brightest bursts happen when supply is abundant and regulation is temporarily overcome. The average growth rate declines with time. The mass distribution broadens because histories diverge. Some centers grow through long, steady phases. Some grow through mergers. Some remain small. The scene returns to the field of beacons. Some halos show sharp edges. These edges are shell boundaries from past winds. Some halos are smooth. Smooth halos suggest gentler feedback or older remnants that have mixed away. The physical details become a quiet code. A sharp rim suggests a recent active phase. A diffuse glow suggests older heating. A central void suggests a cavity still pressurized. The scale shift expands one last time. A shell can persist for tens of millions of years. A quasar episode can be shorter. A galaxy's gas supply can change over 1 billion years. The population record integrates all of this into a few curves and counts. The transition remains gentle. The next section turns toward the heaviest end of the story. The next section follows why some black holes reach 1 billion solar masses, while others stall, focusing on feeding limits and how they can be bent without being broken. The same feeding limit can be bent by geometry and thickness without being broken. The most massive black holes reach their size by staying near a limit for long intervals, and by reducing how strongly light pushes back. In that region, the inner flow is not always a thin, bright plate. It can be thick and layered. It can be wrapped in a scattering cocoon. The cocoon creates an opacity gradient. It is denser near the midplane. It is thinner toward the poles. Light behaves as trapped diffusion in the dense zones. It escapes more freely in the thinner zones. A small payoff arrives early. A high inflow rate can coexist with a modest outward push when radiation escapes along preferred paths. The first concept is the Eddington limit. Eddington limit is when radiation pressure balances gravity for ionized gas. The definition is short. The idea stays calm. If luminosity rises too high for a given mass, radiation pushes gas outward. That push can slow or halt inflow, yet the limit is derived for a simple spherical flow. Real flows can be far from spherical. The second concept is photon trapping. Photon trapping is photons carried inward faster than they escape. The definition is short. The picture is gentle. In a thick flow, the gas is so dense that light scatters many times. Each scatter delays escape. If inflow is fast enough, the photons ride inward with the gas. The outward pressure felt by the inflow can be reduced because photons do not get time to push outward. A small payoff follows. Trapping allows mass to cross inward, while the observed luminosity stays closer to the classic limit. The visual anchor becomes distinct and new. A swollen torus surrounds the dark center. Its surface is a soft, glowing skin. The skin is brighter near the poles where it is thinner. The equatorial region is dimmer because it is thick and shadowed. A narrow polar funnel looks clearer. It is edged by a bright rim where photons last scatter. The physical detail is a sharp funnel boundary and a layered torus wall. Light behaves as a slow seep through the wall and a quicker escape through the funnel. The unique analogy stays calm. A sponge soaked with warm water releases moisture slowly from its dense interior. Along a few open channels, vapor escapes more quickly. The sponge is the thick flow. The channels are the polar funnels. The Gaussian is photon diffusion. The payoff is immediate. The same total energy can have different effects depending on where it escapes. One rounded number anchors the growth target. 1 billion solar masses is like a mountain made of 1 billion suns. The comparison is simple and quiet. The scale shift becomes gentle. Building such a mass takes long intervals of steady supply. The inner flow responds in hours. The host supply responds in millions of years. The cosmic environment changes over billions of years. The question becomes one of persistence. How often can a thick flow be maintained? How long can it stay close to the limit without being choked by feedback? Another payoff arrives. The most important factor is not a single peak rate. It is the absence of long empty gaps. The scene moves to the boundary between thick flow and surrounding disk. Outside the torus, a thinner disk can exist. It feeds the torus through a transition zone. The transition zone has a steep gradient in thickness and temperature. The disk becomes puffy as it approaches the center. Magnetic stress and turbulence heat it. Cooling competes with heating. If cooling is inefficient, thickness increases. If cooling is efficient, the disk stays thin and radiates more. A small payoff follows. Thickness and radiative efficiency trade against each other. A thicker flow can accept higher inflow while appearing less luminous. A thinner flow shines more and pushes back more strongly. The scene returns to the polar funnel. The funnel can launch a wind. The wind is lighter than the equatorial inflow. It carries away energy and some mass. It can also collimate radiation. The funnel wall can be a scattering surface. It redirects light into the polar direction. This can reduce radiation pressure on the equatorial inflow. Another payoff arrives. Feedback can be anisotropic. It can push strongly in some directions while leaving protected lanes for inflow. This creates a pathway for rapid growth in dense environments. The limit of observation enters softly. Thick flows are difficult to diagnose. Their spectra can be heavily reprocessed by scattering and absorption. The emitted light can look cooler than the inner temperature. Orientation can change apparent brightness dramatically. A source seen along the funnel can appear very luminous. The same source seen edge-on can appear dim and obscured. Estimating true accretion rate from observed light then becomes uncertain. Models of photon trapping depend on assumptions about opacity and turbulence. Those are not directly measured in distant systems. This is a limit of inference and of degeneracy. Different geometries can reproduce similar observations. Still, the general physics remains stable. Dense flows can trap photons. Funnels can allow directional escape. Another payoff settles. Bending the limit is not the magic. It is a consequence of layered structure and transport times. Radiation pressure acts where photons interact. If photons are trapped, pressure couples less to the deepest inflow. If photons escape through funnels, pressure couples more to low-density gas. This reshapes the balance without violating conservation laws. The scene widens to the host environment again. A thick inflow is more likely when supply arrives in heavy streams. It is also more likely when metallicity and cooling conditions favour large-scale inflow over fragmentation. In later epochs, supply becomes less continuous. Feedback has more time to clear central regions. Thick flows may be less persistent. This helps explain why the earliest environment can produce rapid giants. It also explains why late-time growth often proceeds in shorter episodes. The scale shift expands one last time. A photon's random walk in the torus lasts many scatterings. The inflow time through the same region can be shorter. Over millions of years, repeated thick phases can add large mass. Over 1 billion years, these phases build the monsters that dominate the bright end of the population. The transition remains gentle. The next section turns toward how growth ends or slows. The next section follows why some black holes stall, how supply changes, and how the universe settles into quieter centers over time. A black hole slows its growth when the supply chain becomes thin and intermittent. The stall is usually a change in environment rather than a change in gravity. In that region, the central reservoir can be heated, dispersed, or locked into stable orbits. Gas can be present in the host and still fail to reach the inner disk. The physical detail is a stratified core. A warm diffuse phase fills the inner volume. Cooler clouds drift at larger radii. A hot cavity may persist near the center with a sharp pressure boundary. Light behaves as a softer, less frequent glow because dense inflow is rare. A small payoff arrives early. Growth ends quietly when gas loses its pathway inward, even if plenty of mass remains nearby. The first concept is angular momentum. Angular momentum is the tendency of orbiting gas to keep circling. The definition is short. The picture is calm. A rotating disk resists falling straight in. To move inward, gas must lose angular momentum through stresses and collisions. If those stresses weaken, inflow slows. The second concept is feedback. Feedback is energy and momentum from accretion affecting surrounding gas. The definition is short. The effect is gentle. Outflows and radiation heat gas and raise pressure. They can inflate a cavity. They can also drive turbulence that stirs and thickens the medium. This can both hinder and reshape inflow. Another payoff arrives. Feedback does not need to expel all gas. It only needs to disrupt the narrow lanes that deliver gas to the inner disk. The visual anchor becomes distinct and new. A hollow cavity surrounds the center like a transparent bubble. Its inner surface is smooth. Its boundary is marked by a thin, bright shell where gas compresses. Outside the shell cooler, filaments break into clumps. The clumps drift around the cavity rather than into it. The cavity acts like a gentle barrier. A signal would fade as it passes through the hot, low-density interior because emission is weak. The unique analogy stays calm. A pond freezes at the surface, water still exists below, yet the ice changes how anything can enter. The ice is the hot cavity and pressure barrier. The water below is the remaining gas reservoir. The channels that once delivered inflow are blocked or rerouted. The payoff is immediate. A reservoir can remain while the delivery mechanism fails. One rounded number frames the scale of influence. An active phase can carve a cavity that spans about 1,000 light-years. That span is like a quiet basin that holds an entire weather system. It is large compared with the inner disk. It is small compared with the full galaxy. The scale shift becomes gentle. The inner disk evolves in days to years. The cavity evolves over millions of years. The host gas supply evolves over billions of years. A short active episode can therefore imprint a long-lasting change on the central conditions. Another payoff follows. A brief bright phase can delay the next feeding episode by a long interval because the core must cool and settle again. The scene moves inward to the edge of the cavity. At the boundary, gas piles up. Density rises sharply. Cooling becomes easier in the compressed shell. Yet the shell also gains angular momentum from the host. It can rotate as a ring. The ring can become unstable and fragment into clouds. Those clouds can collide and lose some angular momentum. If collisions are frequent, inflow can resume. If collisions are rare, clouds orbit and the center stays quiet. Another payoff arrives. Stalling is often a competition between cooling and dense shells and the persistence of rotational support. The scene drifts outward to the larger galactic center. Barr's spirals and asymmetries can transport angular momentum outward. If those structures weaken, inflow to the center slows. In some epochs, the host becomes dynamically calmer. Gas settles into stable disks, merger rates decline. The cosmic web delivers less fresh fuel. These changes reduce the duty cycle. Another payoff follows. The universe ages into quieter centers because the mechanisms that disturb orbits become less frequent. The limit of observation enters softly. Quiescent black holes are difficult to diagnose. Their accretion light is faint and often swamped by surrounding emission. The density and temperature of the central gas are inferred from indirect tracers. The geometry of cavities is inferred from line emission and absorption patterns. Those patterns depend on uncertain heating and chemistry. Time sampling is limited. A single observation captures one moment in a long cycle. This is a limit of sensitivity and cadence. It prevents direct measurement of how quickly cavities refill. It forces reliance on models and population averages. Another payoff settles. Even with limits, a coherent picture emerges. The stall is not absolute. Small trickles can continue. Occasional clouds can reach the inner region. Minor inflow. Events can rekindle a disk for a while. Yet the average rate drops because supply and transport weaken. The mass then grows slowly compared with earlier epochs. The scene returns to the cavity interior. The hot gas is thin and smooth. Its pressure gradient points outward. The bright shell at the boundary slowly softens. Ripples pass along it as outer clouds graze the surface. Some ripples amplify and break into knots. Most fade. The physical details remain gentle and concrete. A ring of cooler gas can form outside the shell. It is thicker than a thin disk. It is supported by pressure and rotation together. The ring can precess and warp. Warps can create brief channels inward when parts of the ring collide. Another payoff arrives. The same structures that stall inflow can later prime a restart by storing gas in dense rings that can become unstable. The scale shift widens one last time. A cloud crossing the central 100 light-years can take thousands of years. A cavity can persist for millions of years. A galaxy can drift through a changing environment for billions of years. Across these times, the black hole's growth is a sequence of windows. Each window opens when transport aligns. Each window closes when feedback reshapes the core. The transition remains soft. The next section resolves the arc by gathering seeds, limits, and long timescales into a calm perspective. The next section settles into how growth histories fit together without urgency, and how the cosmos continues in slow balance. A black hole becomes a monster by repeating ordinary steps for an extraordinary duration. The full story is not one trick. It is a chain of conditions that stay aligned long enough. In that region, growth begins as a seed. It continues through inflow that must lose rotation. It is moderated by light and by heat. The outcome depends on how often the pathway stays open. A calm payoff arrives early. The biggest masses come from long continuity rather than the highest peaks. The first concept is duty cycle. Duty cycle is the fraction of time accretion stays active. The definition is short. The idea is simple. Even a modest rate can build a vast mass if it persists. Even a high rate contributes little if it flickers rarely. The second concept is radiative efficiency. Radiative efficiency is how much energy emerges per unit mass. The definition is short. When efficiency is high, the flow shines strongly. Radiation pressure and heating act more strongly on nearby gas. When efficiency is lower, more mass can pass inward for the same observed brightness. A quiet payoff follows. The same supply can produce different growth depending on how energy is released and where it escapes. The visual anchor becomes distinct and new. A slow mosaic spreads across a dark plane. Each tile is a short episode of the inflow. Some tiles are bright and thin, some are dim and thick. Between them are gaps that look like cooling silence. The mosaic extends across millions of years as a pattern. The center remains a constant shadow. Around the shadow, a faint ring appears and fades. The ring edge stays sharp when the disk is thin. The ring edge becomes softer when the flow is thick and scattering dominates. Light behaves as pulses that rise and settle without urgency. The physical detail is the changing ring boundary and the persistent central shadow. The unique analogy stays calm. A shoreline builds from many small tides. No single wave explains the coastline. The tides are the accretion episodes. The coastline is the final mass. Each tide leaves a layer. Some layers are thick, some are thin. Over long time, the layered result becomes large. Another payoff arrives. Growth is a layering process. It stores history in the mass even when the light is gone. One rounded number anchors the perspective. 1 billion solar masses is like 1 billion suns, gathered into one gravitational center. The comparison stays simple. The scale shift becomes gentle. A single orbit near the inner disk lasts hours. The same black hole can take hundreds of millions of years to gain most of its mass. The host environment changes on billion-year timescales. The universe provides fewer dense feeding conditions as it ages. This places early epochs in a special role. Early on, gas is abundant and compact. Inflow lanes are easier to sustain. Thick flows and trapping can help. Seeds can also be heavier. Later on, gas becomes more settled. Transport weakens. Feedback leaves longer-lasting cavities. Duty cycle shrinks. Another payoff follows. Early growth is often easier than late growth because the cosmos itself is denser and more restless. The scene moves to the boundary where inflow meets resistance. A thin disk radiates efficiently. Its surface is a bright sheet with a steep temperature gradient. A thick flow is puffed and layered. Its opacity gradient traps photons. A cavity is a low-density bubble with a sharp pressure wall. These structures are not separate stories. They are phases of the same system. The phase depends on supply and on transport. It depends on how quickly gas can cool. It depends on how energy couples to the surroundings. Another payoff arrives. The feeding limit is not a single ceiling. It is a set of balances that shift with geometry and time. The limit of observation enters softly. The growth history is reconstructed from snapshots. Distant bright sources are easier to detect than quiet ones. This biases samples toward active phases. Mass estimates can be uncertain because line widths and surrounding emission complicate inference. Obscuration can hide luminous phases behind thick material. Orientation can make the same object appear different. The true duties cycle is therefore hard to measure directly. This is a limit of selection and of indirect modelling. Yet the broad arc is supported by multiple lines of evidence. Massive black holes exist early. They require sustained growth. They require either heavy seeds or long near-limit accretion, sometimes both. Another payoff settles. Uncertainty in details does not erase the main requirement. Time and continuity remain the central currency. The scene relaxes outward. A galaxy core appears as a soft glow. The central shadow remains invisible directly. Its influence appears in orbital motions and in the shape of surrounding gas. A faint ring of warm dust can mark the inner environment. Farther out, filaments drift like slow currents. The entire structure breathes on long timescales. In that region, nothing needs to rush. Gravity works steadily. Light responds to whatever gas happens to arrive. When supply is rich, the inner region brightens and reshapes its surroundings. When supply fades, the core cools and quiets, the mass remains. The story continues in suns. Another payoff arrives. The most durable sign of growth is not the flare. It is the accumulated mass that persists after the flare. The final scale shift widens to deep time. The early universe offers dense fuel and short paths. Mid-time offers episodes and regulation. Late time offers long pauses and gentle maintenance. Across all stages, the same principles hold. Rotation must be redistributed. Energy must find an escape route. Gas must remain available and coherent long enough. The resolution is calm. Seeds set the starting point. Feeding limits set the pace. Geometry and trapping shape how limits are experienced. Duty cycle decides the total. The landing is soft. The next moments do not open new mysteries. The pattern simply rests. In that quiet rest, the cosmos keeps its slow rhythm. The largest black holes remain as stable anchors in an ever-cooling universe.